Today, we're going to pull back the curtain on something we all use every single day, but maybe don't think about too much: the power grid.
You know that feeling? You flip a switch, the lights just pop on. It feels so simple, right? Almost like magic. But what's really happening behind that wall? Well, the journey that electricity takes it's incredible. So let's trace it from the place it's made all the way to your home.
Okay, so everything starts at the source, right? The power station. Now sure, there are lots of ways to make electricity these days, but when you look at the big picture, the real heavy lifting, that's done by three main types of plants.
All right, first up, we have the absolute workhorse of the grid, the thermal power station. And at its core, the idea is surprisingly simple. Seriously, just picture a giant, super high-tech kettle. It basically works on a principle called the Rankine cycle.
And it's really just a big loop. You burn fuel, usually coal, to boil water. That creates this incredibly high-pressure steam. This steam then just blasts through a huge turbine, spinning it like a crazy fast pinwheel. That spinning motion is what drives the generator to make electricity. After that, the steam is cooled back down into water, gets pumped right back to the boiler, and the whole cycle starts over. The leftovers? Ash and flue gas.
Okay, so from burning stuff for heat, let's switch gears completely and talk about height. I'm talking about hydroelectric power. This is a totally different game, all about harnessing the incredible energy of water that's just sitting there, waiting, behind a massive dam.
And of course, like with anything this big, there are pros and cons. A huge pro: hydropower is clean. You're not burning anything. And it's super responsive. You can basically flip a switch and get power instantly. But the downsides are pretty big too. Building these things costs a fortune. They're often in the middle of nowhere, so you need long transmission lines. And the biggest one? You're totally at the mercy of the weather. If you have a dry season, well, that can be a real problem.
All right, our third heavy hitter is the nuclear power station. Now this one's interesting because it's kind of like a thermal plant. It uses heat to make steam, to spin a turbine. But how it makes that heat, that's where things get radically different. Forget a coal boiler, we're talking about a nuclear reactor. So deep inside that reactor, you have atoms of uranium-235 being split apart. It's a process called nuclear fission, and it releases just an insane amount of heat. Now this is a very controlled reaction, managed carefully with things called moderators and control rods. The upside here is huge. The running costs are super low. But the downside, well, it's the one everyone knows about. What do you do with the radioactive waste? That's a massive, massive challenge. Okay, so we've got these incredible power plants ready to go, but they're all up against this one constant, relentless problem: us. Our demand for electricity is all over the place. It's constantly changing, all day, every day. And to get a handle on this challenge, the folks who run the grid use this really important tool. It's called a load curve. It sounds technical, but it's really just a simple graph that gives them a perfect snapshot of our collective energy habits. And this is where it gets really cool, because this one graph tells the story of a typical day for all of us. You can see it right here. The demand, or load, is super low overnight. Obviously, we're all asleep. But then, look, around 6 a.m., boom, alarm clocks, coffee makers, showers, the demand shoots right up. It might dip a little in the middle of the day, but then comes the evening. We all get home, start cooking, turn on the lights, watch TV, and that's when the demand hits its absolute peak.
That huge evening spike, that's what the industry calls maximum demand. And this is the key to everything. The entire power grid, every single power plant, every wire has to be built big enough to handle that one single moment of highest demand, even if that peak only lasts for an hour or two. Think about that. It's a huge deal.
So, that's the big question, right? How on earth do you manage a system that has to deliver a steady amount of power 24/7, but also be ready for those massive, short-lived spikes? Well, the answer is actually pretty clever. It's all about a division of labor.
And the best way to think about it, honestly, is like a track team. It's a great analogy. You've got your base load plants. These are your marathon runners. They're built to just go and go and go, running steadily and efficiently all day long, covering that minimum level of power we always need. And then you have your peak load plants. These are the sprinters. They're sitting on the sidelines, ready to jump up and give a quick, powerful burst of energy to handle those big spikes when they happen.
And why do we do it this way? Well, it all comes down to money, to economics. Your baseload plants, your nuclear and coal plants, they cost a ton of money to build, but their fuel is cheap, so it makes sense to run them all the time to get your money's worth.
On the flip side, your peak load plants, think gas or diesel turbines, they're way cheaper to build, but the fuel costs are much higher. So you only want to fire those guys up when you absolutely have to.
So you've got this team of marathon runners and sprinters, but how do the coaches, the grid engineers, know who to put on the track and when? How do they make sure the whole thing is running smoothly and not costing a fortune? Well, they have a few key numbers they're always watching, like the grid's vital signs. Let's take a quick look at what they are.
First up is something called the load factor. And here's an easy way to think about it. Imagine you own a car. If you only drive it for 10 minutes once a week, that's a really low load factor, right? It's an expensive thing that's just sitting in your driveway. But if you're a delivery driver using that car 8 hours a day, you've got a high load factor. For a power plant, a higher load factor is always better. It means that giant, expensive investment is actually being put to good use.
Okay, next up is the diversity factor. And honestly, this concept is fascinating. It's built on a really simple truth. We don't all use our electricity in the exact same way at the exact same time. I might turn my oven on at 6 p.m., while you turn yours on at 7 p.m. Our individual peak times are different.
So because all of our individual peaks are staggered throughout the evening, if you were to add them all up, that number would be way bigger than the actual peak the power station ever has to deal with at any single moment. That's why the diversity factor is always a number greater than 1. And let me tell you, this is a huge deal. This is the whole reason the power company doesn't have to build a grid big enough to power every single house and business going full blast all at once. This diversity is what makes the whole system work without being ridiculously expensive.
And finally, there's the plant capacity factor. This one kind of ties everything together. It's the big picture view. It looks at the average power people are actually using and compares it to the total amount of power the plant could produce if it were running at 100%. Basically, it tells the engineers how well they're using their entire investment over the long haul.
Okay, so we've thrown a lot of terms around. Load curves, diversity factors, capacity factors, and you might be sitting there thinking, all right, that's interesting, but why should I care? What does this have to do with me?
Well, the answer is actually really simple. It all hits you right in the wallet. Every single one of these decisions, which sprinter plans to fire up, how to manage those peaks, how efficiently the whole system runs, it all directly affects that number on your electricity bill at the end of the month.
You can see this super clearly with big industrial customers. A lot of them are on what's called a two-part tariff. This means they get charged for two separate things. First, they pay for their maximum demand. That's a fee for just having the grid ready to supply their peak power needs. Then they pay a second fee for the actual amount of energy they used. It perfectly mirrors the two big challenges of the grid, being ready for the peaks and delivering the total energy.
And that really brings us to the big question for the future. We've seen that the grid is this incredible non-stop balancing act. But think about it. We're starting to electrify everything. Our cars, our heating, everything. This means those peaks on the load curve, they're only going to get higher and more extreme. So the real question we have to ask ourselves is, how is this amazing system going to adapt and evolve to meet the peaks of tomorrow?